back for this last part of Buffet-4. We are going to start with MALBEC. That's going to be presented by Chef Geronimo Villanueva.
Yeah, hi, Tomaya. So we're gonna present actually the three of us, myself, Eleonora, and Stella gonna present for the Malbec. And I'm gonna just give you first of all, a little bit of update first about, you already know about the Malbec, but just to remind some of the things, and go to updates, and then we're gonna go to the two subgroups. We have direct imaging and transit. So let's go for that. Sorry, there we go. So what is the philosophy and the teams? So the main idea that we wanted to do in this particular thing is you probably hear everywhere about there are different right transfer codes. And I think at the end of the day, a lot of them share a lot of similar physics. So I think if you do spend a substantial amount of time, you may be able to make them all converge in some capacity. So one of the things we wanted to do is that we don't want to do that. We want to do otherwise, like what people normally do. They go to the website, they download a model, they run it, and then they get some results and publish that. So we wanted to use the models as people normally use them and see how far they differ for the same task. And that is a different approach than otherwise, but it's normally what we see more differences or what we see more things people different in the models. So the main idea is to understand, first of all, where we disagree. We don't want to force it agree. I mean, of course, we're gonna make sure that we all agree in the units and some basic things, but we want to make sure that every code at the end of the day remains as it is. We can improve our codes, that's fine, but we wanna understand why they disagree. So people want to run their codes, they say, oh, look, this is wiggle here, and that is explained by this phenomenon. So you heard that we have these different multiple configurations and modeling schemes, and we're gonna be some models are more trained or more prepared for specific cases. Other models are prepared for more. So we're trying to be a little bit inclusive in that sense to the different techniques, and you will see more when Eleonora and Stella presents their results. So I wanted to make, and we presented a lot last year, but I wanted to remind about this. So this is an example of actually, it's a great paper about, they pick a few codes here and they made a comparison about these codes. And this is an example of in a different approach that we do. In this particular case, they took the codes and they heavily homogenized them to actually operate pretty much the same. So they used the same line list, everything was the same. So the remaining differences were very subtle, and they were more about retrievals. They wanted to see how the bias is in the thing. In the way, that's a way to approach it. In the way is that typically we found is that people use one right transfer code, they use their own line list, they use different approaches. We wanted to keep people use their own approach, and that is more descriptive what people are normally using the models for. So you can see here the level of difference are very, very small, and it's mostly numerical noise, how one code does a slightly different road transfer, but all of them were using exactly the same cross sections, the same layering scheme, they force the codes to do everything the same. So pretty much the main difference were numerical, but beyond that, and it's interesting what is being found here in this paper, but we wanted to go beyond that. We wanted to say, okay, let's let the codes do, okay, I'm gonna give you a giant planet, model it out, tell me what you see. So, and then this is the codes, and there is, as you can see from all these codes, they come in all colors and flavors, and they're very different in their capabilities and what they're, the heritage. Some of them are based on Earth models. Some of them come from astrophysical side of things, for stellar astrophysics. Some of them have, 3D, 1D, so they are going to be very different. Some of them are for transit, some of them are for direct imaging. So, you can see these all of them, this is the initial team, and this is appear in the protocol paper. But, some of the teams have been more involved, and you will see more from the results that Stella and Eleonora are going to present. You will see that we are mostly focusing on a few codes as the core for this work. So what we do is we still meet one hour every month. Typically what we're doing is we have a general thing, and then Stella and Laura will run their sub teams. We already agree on the input files, and we focusing the exercise by exercise. We have all the parameters set already by this MALBEC input file, and we put everything on the Google Share Drive, the input files and the output files, so people can actually run a simulation and compare quickly to see how far they are, and keep running. So that speed up things up, because you don't have to blindly release a file and then hope that you didn't make a little mistake on there. So the protocol paper was accepted. I'm going to show. So as you know very well, it was accepted this year. So that's great. So being the protocol paper out, what we are doing, focusing right now, is we have one paper for direct imaging. This is the one led by Eleonora, and then one paper developed for transit, and we'll hear more about that by Estelle. So this is just a reminder how the input file for the MALBEC files, this is we've been tweaking the format, but I think it's pretty final at the end of the day. We have a header, and we have all the parameters in SI units, in different ways to parameterize the atmosphere too. So again, every code will ingest this, and some codes that do sublayering, divide the atmosphere in little pieces. Some of them use analytical functions for the atmosphere. Some of them are 1D, some of them are 3D. Some of them are plane parallel. Some of them are full spherical. Some of them are only doing transit. Some of them are doing imaging. So the models are very different in how they're gonna treat this, but all of them should be able to ingest this file. So for the main things that we kind of set in motion when we were defining the protocol, this table appears actually in the protocol paper, these are the main things we've been kind of focusing. First of all, Rayleigh, which is mostly define how people model Rayleigh. Most of them use a very simple lambda to the fourth correction, and they use different parameters. We have seen differences in how that is done, but generally it's pretty good agreement, I must say, typically with Rayleigh. But there are like offsets, and you can see this is because people use different coefficients for the Rayleigh molecules. Then we have found a lot of difference with the isotopes, and that has to do with the line list. Some people use, for example, the ExoMol line list, which is mostly the main isotope, and all the other isotopes are missing. So, how people will combine line lists and all that is what abundances they're going to use for the isotopes, all that. We have noticed a lot of differences there. We also found a huge amount of difference between if the codes do correlated K tables or cross sections, very fine cross sections, or line by line. Probably it's the biggest source of discrepancy within all the codes. Some codes are more flexible and they can ingest different techniques. Some of them are developed only for a specific method. And that also, we're already aware of it, but it's, again, as we say, we're going to let every code does it as their own way. And then we're going to compare and see, okay, if you see that thing feature there, remember that's probably related to that problem. And then also collision-induced absorption. We in general, I think we agree in that. I think we have general agreement. The only thing that has been a little bit different is, and Eleonora will probably show more about that, is the water continuum. We call it MTCKD. We have provided for the group, PhD, we use a technique, and we were using that across. So if you all use that, we tend to agree, which is a good thing. So I think in general, we are in agreement with that aspect of the investigation. So this is the paper. It got accepted in March this year, so we're very, very happy. And again, it's just a protocol paper. We do describe it with, some examples very lightly, but kind of, as you know, we set the foundation for the actual work. Gonna happen in the coming two papers. Just to remind you, this is the KST3B, and this is the one that we compare the other models, and still gonna show more about this, but you can still see there's a high level of disagreement still. We're very happy when we get to this stage, but we are still disagreeing a lot. It's fine, and it mostly has to do with the line lists, how the codes are digitized in the atmospheres, and how if the collision-induced absorption on the line wings. And still, I want to show a little bit more about this. And okay, so back to the two big sub teams that we have now. So we have the transit case. This is led by Stel, and you can see we have a mixture of terrestrial planets. We also have a theoretical case that she will talk about. This is actually has been very challenging, but a great exercise. And we also, but it's transit, we mostly focus on the I would say the heavy or the gas giants, even though we also have TRAPPIST there. And for the direct imaging case, this is where we mostly focus on Earth-like. We also have GJ1214b, infinite atmospheres as a good exercise, and Eleanor will show more about them. So with that in mind, I'm gonna give it to Stella. Go ahead. I can move the slides.
Okay, great. Thank you so much. Hello, everybody. Thank you for having me. So I'm going to talk more about the transit cases. So next slide, please. Okay, so these are our core cases and the other cases. The core cases are meant for, as many of the codes as possible. And we'd like to have as many of them participating and have this comparison. And then the other cases is if your code is compatible with this type of planet, like can we compare it and can we add more subtleties about the differences that we didn't find in the core cases. So the core cases are this layering and ray tracing test that Jérémy Lecomte and Geronimo put together, and that I'll talk about a little bit more in a minute. And then the second one is T3B. Both are based on GJ1214b. But in the case of T3B, we have like an actual extended atmosphere with H2, helium, water, and methane. And in both cases, we're not including clouds. In the other cases, we have, a terrestrial planet, TRAPPIST-1e, that most codes have run by now as well. And then T3C, which is basically the T3B case, but with clouds, that we haven't really started properly yet, but is probably, meant in the next few months or so. And then T4A is the case that was included in the Barstow paper that Geronimo talked about, that we'd like to implement as well to make that connection with this previous intercomparison. Next slide. Okay, so Geronimo showed this figure already, but this is kind of, the best that we had at the time of the protocol paper. And you can see that we have a good general agreement, but we're trying to nail down all these like small differences that are still, in the magnitude of the spectral features and the continuum. If you go to the next slides, the way we're doing this is we have like subcases that we're asking codes to run. So for example, this is the case with only molecular absorption, which allows us to nail down the differences that are specifically due to, line-list and opacities as opposed to CIA or Rayleigh processes. If you go to the next slide, this is a summary of the subcases that we've nailed down to try to point out these differences a little more specifically. So we have molecular absorption, CIAs, Rayleigh, and then for codes that include them, absorption from isotopes and water continuum. If possible, there are some codes that can also run both cross-sections and correlated K-tables, and this has been insightful to point out the difference between the two. And then have a closer look at the UV and optical treatment for sub-1 micrometer wavelengths. We've actually, and this is something that we've already solved, but a lot of our initial disagreements were actually due to physical constants, and just the solar constant or the diameter of the Earth, or Jupiter, if this is what your code standardizes to. So it was interesting to see those differences coming up. And then this is, Geronimo also already talked about this list, but this is what we're investigating exercise by exercise. If you go to the next slide. So for example, this is a zoom in section of the T3B case. And you can see that, despite the general agreement, we have small differences in the magnitude of that line at 3.2. And then at 3.7 here, we have differences that we've been able to identify as being from a combination of the water continuum and the H2O isotopes. So little by little, we are getting to these differences and pointing at, where small differences like that can arise. And then, so T3B doesn't include CO2, but for the T1A case, we also pointed out that if you don't include the CO2 isotopes, then the breadth of the line at 4.2 also differs quite a bit. If you go to the next slide. Okay, so T0A has been a very insightful case to focus on, and this is basically a case to look at the layering schemes of the different codes. It has a very simplified temperature pressure profile, and the cross section is basically linearly increasing with wavelength, and is supposed to be like a very simplified water cross section. So we don't include any, absorption besides this water absorption, no Rayleigh, no CIA. And it's meant to really, it shows all the differences in the layering schemes. So you can see, for example, on the left that this is the difference for 50 layers. And the differences that we see are basically due to either, your code takes the average pressure values at the middle of the layer or the boundaries of the layer, whether you have a sublayering algorithm that's implemented in your code, how many sublayers your code interpolates to, et cetera, et cetera. So by describing, all these sublayering specifics of each code, we've been able to little by little understand these differences. And you have codes, for example, like Exoplanet that have a pretty each layer is going to have like a different continuum, or codes like GCM CRT that have like the 20 layers is pretty much the only outlier, and then all the rest of the layers agree. And PSG has a very strong sublayering algorithm, so you basically don't see any difference between the layers if you don't deactivate the sublayering algorithm. And then you have codes that can go up to 1,000 layers, and you have codes that have a limit at 70 layers. So there's a lot of differences in that space to investigate. Go to the next slide. Okay, so going forward, we're focusing on these core cases and trying to really nail them down before the end of the year, especially T0A in the next few weeks. Thanks to this MALBEC file, it's actually really, it's pretty straightforward for new codes to still join at this case, because when you find a way to ingest that MALBEC file properly with your code, you can run a lot of these cases. So everybody's welcome to join, and we're still welcoming new participants. And this is a link to the drive and to the early paper that are, being developed little by little. Eleonora, I hope I didn't take too much time from you, but yeah. Let me know if you have questions.
No, and thank you, Stella. And I must say that Stella is doing a great job leading this. It's a very complicated effort, but for some of the T0A has been, it's very difficult to put everybody work on that, but it had led to a lot of improvements. Actually, some of the things that Stella was saying, it led to improvements in PSG. So, as we compare, we all improve with the code. So it's a gain for everybody, for the participating people. Yeah. Yeah. Okay. Thank you. We can go for questions later. Let's go to Eleonora. Eleonora, you can go.
Yes.
I can move the slides.
Yeah, great. So no worries for the time, because I will not take too much time. This is an effort that's much more recent than the previous one. Yeah, okay, very fast. Too fast. Fine, okay. So it's much more recent, and so there is not a lot to discuss at this point. We're still trying to iron out some kinks, but essentially what we've been doing so far is trying to compare the direct imaging case, which was useful a lot for, especially when it comes to the missions that I'm personally involved in, like Life and Habitable Worlds. So I had to do this kind of intercomparison for my own research as well. Next slide. So the main thing with the direct imaging is the treatment of the reflected light part, so the stellar radiation specifically. And there are two main camps that the codes might follow. Like they could be either a 1D treatment or a 3D treatment. And we noticed this because we were comparing Perdita Trans, which is the code that I'm currently using, and PSG. And we encountered some issues as the results didn't match, and we wanted to figure out exactly why. Well, essentially the issue is that in the case of PSG, as you see in those images, you can you treat the disk of the planet as a 3D object, and so you have various regions that are illuminated differently by the light of the star. So it's more, in a way, more high fidelity, if you want, compared to truth. On the other hand, from Petit-Trans and other codes that follow a 1D approach, you have a one single column when you get the light coming from the star, and then you scatter more or less isotropically, or you can make some assumptions on how the light gets uniformed throughout the atmosphere, but you're ultimately just assuming a 1D. And so the interface between those two is that the 3D case needed two angles. So the solar incidence angle and the observing angle, while we only, in Petit-Trans, we only use the solar incidence angle, or some sort of angle that we were not really sure what that meant at that point. So if you go to the next slide. Actually, go to the next for a second. And so when trying to compare this for the first time, at phase 90, these, you can see I tried a lot of different options with Petit-Trans at phase 90, and none of them would compare with PSG. They were, especially in the shorter wavelength range where you have the reflected light, they were not comparing no matter what I was doing. And so if you go back. Right, so we figured out that the issue was related to, basically we related the phase angle to the the phi. So we have found like an average angle that we could use to connect the 3D models with the 1D models. So I could use phi g in my 1D model to represent the average irradiation that the planet would receive. And that would just essentially average out throughout all the latitudes and longitudes in the 3D object that we were not considering otherwise. And so if you go forward twice, this is the phase 180, which was, we turned off the light from the star, so no issues there. A lot of different codes would match to some extent. There are some small differences, but the biggest, there is quite a good agreement. And if you go one forward again, this is the new phase 90. So now finally we can match all the models, because we have this added, this added knowledge that we know how to connect the 3D models to the 1D models. And actually this, when reaching out to the Petit-Trans developers, they were impressed that we could get to such high agreement, because, as I said, Petit-Trans was not built for that. And so this was another piece of knowledge that nobody actually ever knew. And I feel like this could be a good item to write on the paper eventually. And so the last picture I think I have is phase 0, same old, we're just changing the phase of the planet, so it still works just fine. It just changes the intensity of the reflected light part. And I think that was it.
Thank you, Lorena. And I have to say, I wanted to show this plot, for example. That was very diagnostic, because we used this plot to, I would say, calibrate the models. Even though they look at agreement, initially they were not agreeing because we were disagreeing on the units, what is the steradian they are doing and all that. So it took a lot of work to get them to agree on that. And using the thermal was a good guide for us to calibrate the fluxes. And then you can see these ones are already agreeing pretty well. So it looks pretty. And sorry, Lerna, P3 is the Petit-Trans free, or what is P3?
P3 is Jeremy LeConte.
Jeremy LeConte. Okay, that is great. And again, each of these codes are doing things very differently. I mean, some of them are using multiple scattering, are using different scattering approximations. The fact that they agree so well is very, very reassuring. Okay, so what is the outlook? What is happening in conclusion? So the group is great. I have to say, as you see, this is a very kind of tedious, because you have to go for this and you have to go into every code, into the details. But I think it's a great group, and I'd say Eleanor and Stella are doing a great job in leading those two efforts. So I think it's going to produce high quality papers. I think, as Eleanor was saying, some of these things will actually help the Petit-Trans, for example, teams to showcase their model. So we have now the paper is published, and now, as we said, we're working on these two papers happening now, and we have initially, we don't actively work a lot with the other MIPS, but we try to integrate the feedback, but certainly open to work with other MIPS. And I think the one that we have, I would say the closest connection is with risotto, with Amber's, because, you know, of course, we are the forward side of thing of the risotto. So I guess this is, you know, many of us are involved in risotto, but we also want to be involved with other MIPS. So, you know, we finalized here, we definitely open to other collaborations and other MIPS. So that's from our side.
Awesome. Well, thank you very much to the three of you. That was very interesting. That's a massive effort, and that's very important work. We really see that we are finding a lot of interesting things and differences, and I'm sure that the more we are going to go into the papers, the more we're going to find some stuff that definitely impact the synthetic spectra. So yeah, that's very important.
Thank you.
We have a question from people in the audience.
Adib and Amber. Yes, yep, Adib.
Yeah, great. Thanks, guys. That was great. Question for Eleonora. Really fascinated by your finding of the angles that you could use in order to approximate that 3D effect. I'm curious if you compared that with running Petit Rattrans basically in a column mode for every column in like an input GCM to see how that compared with running on your unique angles.
I have not actually an interesting idea. We could try and do that. However, I've been in a way discouraged by the Petit Rattrans devs to just stretch the model any further. But I mean, in principle, it could be an interesting study per se. Yeah, that could be cool.
I asked because for Exoplanet, when I had to use Petit Rattrans to do reflection spectra, that was the approach I used, and it's computationally very expensive compared to doing a single run on a unique angle. So I'm curious to see
if you have the framework ready, be my guest.
I can email you some code, sure.
Yeah, sure, great.
One comment about Adib. So for some, there's a paper actually led by Thomas that is under review right now. That we did it with PSG, but it's at the end, as you can see, they are the same once you use it, and we compare the multiple points to 1 point. I mean, it works for when the scattering is not that crazy. You can get a pretty good agreement. It's not perfect when you go to this highly scattering mode, but for the sake of simplicity, I would say it's pretty good. I mean, in Thomas' paper, we cannot quantify a little bit about it, but yeah, you can certainly run it with Petit Rattrans, yeah. And
Amber?
Hey guys, yeah, fantastic work. I'm really inspired by how in depth you guys have gone with each of the different studies and how it has naturally progressed into sort of sections that kind of are appropriate to each type of observation and everything. It's really great. I wanted to dig in a little bit more, and this might be a question for Estelle in terms of like when you're figuring out certain differences between the models and going back into like the sublayering and different molecules or things that were added versus not. How did that kind of come about into like figuring out those differences? Was it a matter of adapting and putting out new config files that were like turn on and turn off this thing, or what was your approach there?
It's a lot of trial and error. So we basically have like a stepwise process where first all the codes try to do the same exercise, and then we go like 1-to-1 with each code to try to figure out like differences, usually with respect to PSG, but it can be with any like pairwise codes. And for the sublayering in particular, something that helped was in the PSG MALBEC value, you have like an altitude column, and sometimes some of the differences were linked to this like the verticalization. I don't know if this is a word, but basically if you implement like pressure, how the pressure versus altitude is translated. And so if you ingest like the altitude directly, like does that solve some of the differences? Also, if you force your code to take the pressure values as the middle of the layer versus the boundary of the layers, like does that solve some differences? And we were able like that to kind of piece together some of the contributions, but we haven't nailed down like all the differences, but it's definitely like a trial and error process for sure. And then some of the codes like have hard-coded limits, like the number of layers, or like the sublayering algorithm and the number of layers they can like interpolate. And so for that, like you just have to, like just pinpoint that this is the cause of this difference, and then like have your best intuition for the explanation, because you can't test it further.
Yeah, okay. That's definitely good to know. I think we'll definitely see some sort of cascading effects into the retrieval models in terms of like whether or not what the assumptions you're making for the profiles, whether they're constant or not, and kind of that vertical structure that might come about. So thanks for the insights. Appreciate it.
Yeah,
Small comment. I mean, one of the great things about Esther's paper, when it will document, for example, you can see the sublayer produce like an offset, like if you see your models having an offset, you will pretty much know that that is a sublayer problem. But for example, if you see, as Estella was saying, if you miss this little wiggle there, well, that's an isotope problem. And so at least, I think the paper will be a guide there for people to know. If you disagree, it will tell you, oh, that's probably, it's kind of a, like a guide there where so which is a great asset for the community.
Last question from Aurélien, after we will move to Samosa.
Hi, yes, just a question about the 3D part of the comparison. So that's very, very interesting, actually. What my question is, will you consider phase curves, light curves, transmission, emission, or what is the future of this comparison? Like we discussed with Alice Morel in the chat also about this comparison, like with Atmosphere and PSG, for example. And we would be interested, I guess, in doing that in the future. So I don't know if it's in the works or what.
Yeah, Eleonora is probably stuck in another meeting. She has like 2 other meetings going on. So yeah, yeah, definitely. So right now for the specific paper led by Eleonora, right now we are focusing on phase zero, which is geometric albedo or front of the star. Then quadrature, which is the prime observational mode for direct imaging mode or coronagraph. And then we're doing 180, which is nighttime, which is secondary or eclipse, and it's also good diagnostic. We use first the nighttime to get the fluxes right between the models, and then we migrate to the CETO, which is the easiest of all of them, to get the geometric albedo calculation right. That one is so embedded into models because that is the energy balance calculation effective. So we need to agree on that. And once we agree on the nighttime, on the energy balance, which is phase zero, then we go to 90, which is a coronagraph mode. And this is where we find more disagreements. But at the moment in the paper, we have those 3 phases as the prime investigation phases.
Yeah, thank you, G. I lost my unmute button for a second. I'm sorry. Yeah, so I agree with what you said. There is a very low work in progress, phase curve analysis that we're doing between Pereira Transit, PSG, but at this point we were sticking to the main 3 phases. Also, because at this point we would like to have more, participation from the codes. Right now the participation is relatively low for this. So before adding to it, we wanted to have this little milestone first. Yeah.
Thank you.
Okay, well, thank you again to the MALBEC team. And now let's move on to Samosa.